Some alcohols like ethanol can be prepared by the fermentation of sugars. Energy released in the fermentation reaction is used by microorganisms for their life processes. Fermentation is an alternative to breathing and occurs in anaerobic conditions. The fermentation of sugars by yeast, the scientific name of which is Saccharomyces, produces ethanol and carbon dioxide. The process is carried out by adding yeast to a mixture of sugar and water. The fermentation stops when the concentration of ethanol in water reaches 12 to 15%, because ethanol deactivates the yeast enzymes. Ethanol is recovered from the reaction mixture by distillation. It distills as the minimum boiling azeotrope, containing 95% ethanol. The preparation of pure ethanol, called absolute alcohol, requires additional purification methods. Ethanol is the active component of alcoholic beverages. Some of them, containing a low percentage of alcohol, like beer or wine, are produced by the direct fermentation of natural products, barley, grapes. Ethanol is toxic, but much less so than methanol. It has hypnotic properties. It depresses brain activity and induces sleep. Alcohol abuse is a major drug problem in many countries around the world.
Hydration of alkenes is a general synthetic method for preparing alcohols. The addition of water to the double bond is catalyzed by acids and proceeds in several steps. The first step involves the formation of a carbocation. The carbocation reacts with water, followed by removal of the hydrogen ion. As the reaction proceeds through the carbocation stage, it follows Markovnikov's rule. Therefore, it can be used only for the preparation of secondary and tertiary alcohols. An example is the hydration of propene that yields 2-propanol, a secondary alcohol, whereas the hydration of 2-methylpropene in the presence of acid yields a tertiary alcohol, 2-methyl-2-propanol, as a major reaction product.
The alternative synthetic route to the alcohols is the nucleophilic substitution of haloalkanes. The halogen atom can be replaced by a hydroxyl group in the reaction of the corresponding haloalkane with hydroxide ions. The ease of substitution of haloalkanes increases in the order fluoride, chloride, bromide, and iodine. Therefore, bromo and iodoalkanes are preferred for the synthesis of alcohols. Substitution reactions of haloalkanes can be used for the synthesis of primary, secondary, and tertiary alcohols. For example, the reaction of 1-bromopropane with aqueous sodium hydroxide yields propan-1-ol, while 2-bromopropane yields propan-2-ol under the same conditions. The synthesis of primary alcohols occurs via the biomolecular SN2 mechanism, while the synthesis of tertiary alcohols proceeds according to the SN1 mechanism, with formation of a carbocation intermediate. Secondary haloalkanes can react by both mechanisms. SN2 reactions are preferred, since they are not accompanied by rearrangement side reactions. Polar aprotic solvent and a high concentration of hydroxide ions favor the SN2 mechanism. The other method for the preparation of alcohols involves Grignard reagents. Grignard reagents are formed by the reaction of haloalkanes with magnesium in an anhydrous diethyl ether solvent. The carbon-magnesium bond in these compounds has a partial ionic character, with partial negative charge on the carbon atom. This carbon atom can attach itself to the partially positively charged carbonyl carbon atom of aldehydes and ketones. Reactions between Grignard reagents with carbonyl compounds, followed by acid hydrolysis, can yield alcohols of different classes, depending on whether the carbonyl compounds are aldehydes or ketones. The reaction of a Grignard reagent with methanal, followed by hydrolysis with an aqueous solution of hydrochloric acid, yields the corresponding primary alcohol. If ethyl magnesium bromide is used, the corresponding primary alcohol produced is propan-1-ol. When other aldehydes besides methanal are reacted with Grignard reagent, secondary alcohols are obtained. For example, if ethanol is reacted with ethyl magnesium bromide, the secondary alcohol, butan-2-ol, is obtained. Ketones yield tertiary alcohols by a similar reaction. For example, the reaction of methyl magnesium bromide with propanone gives the corresponding tertiary alcohol 2-methyl-propan-2-ol. Let us plan the synthesis of the two alcohols propan-2-ol and 3-methyl-butan-2-ol, starting from the same substrate, 2-bromopropane. The preparation of propan-2-ol from 2-bromopropane seems quite straightforward. It can be done by heating 2-bromopropane with a dilute aqueous solution of sodium hydroxide. How could we prepare the other alcohol? Notice that the reaction of 2-bromopropane with magnesium in a diethyl ether solution gives the Grignard reagent 2-propyl magnesium bromide. The subsequent reaction with ethanal, followed by acid hydrolysis of the product, should give the desired 3-methyl-butan-2-ol.